Welcome everyone to this highly focused explainer. Today we're going to completely master the application layer from the ground up, getting you fully prepped and confident for your exams. I am absolutely thrilled to guide you through this material. If you've ever found yourself wondering exactly how the apps on your phone or your laptop actually talk to the internet, well, you are in the exact right place. We're going to build your understanding step by step to really lock these concepts into your memory. Let's get into it.
Okay, so here's our game plan for today. We'll start by defining what the application layer even is. Then look at how these apps communicate. Check out the two main architectures they use, figure out what services they need from the network, introduce our good friends TCP and UDP, and finally, we'll wrap up with a quick fire Vivo revision to test your knowledge. So let's dive right into our first topic, getting a clear picture of where exactly we meet the network.
You know, the application layer is actually the home of literally all the programs you interact with on a daily basis. As a user, you don't really interact with routers or massive fiber optic cables under the ocean, right? No, you interact with WhatsApp, Gmail, YouTube, Netflix, and your web browsers. The application layer is the absolute topmost layer of our network model. It is the direct interface between human users, like you and me, and the insanely complex global network running underneath. Every single time you send a text or load up a web page, an application layer protocol is quietly working behind the scenes to make it all happen.
Right, moving along to our next concept. Let's peel back the interface and look at how these applications actually talk to each other. To really understand this, we have to talk about processes. A process is, very simply, a program running within a host device. Now, when two processes are on the exact same machine, they just talk using rules defined by the operating system. Easy. But when they're on entirely different hosts separated by the internet, they have to communicate by exchanging messages. And there are two very distinct roles to remember here. The client process is the one that kicks things off. It initiates the communication. Think of your web browser actively asking for a website. On the flip side, the server process is the one that patiently waits to be contacted, kind of like a web server just sitting there waiting for your browser's request.
And this brings us to a massively important, highly testable concept for your exams, the socket. Listen, a process cannot just throw a message directly out onto the internet wire. It doesn't work like that. It has to send it through its socket. You can think of the socket literally as the door through which a process shoves a message into the internet infrastructure. Once that message is shoved out the door, the application washes its hands of it and relies entirely on the transport infrastructure on the other side to safely deliver it to the receiving process's door. But here's a question. How do we actually find the right door out of billions on the internet? Well, this is where addressing comes in. To deliver a message properly, you need two distinct pieces of information. First up, you need the IP address, which is a unique 32-bit identifier for the host device. Think of the IP address like the street address of a really large apartment building. But getting to the building isn't enough, is it? You need to know exactly which apartment to knock on. That is your port number. For example, if a server is running a standard web page, it's always listening on port 80. If it's handling email, it's listening on port 25. You absolutely must have both the IP and the port to communicate successfully. Okay, now that we know how they talk, let's look at the foundational blueprints used to build these network applications. There are two major ones you need to know. The first is the classic client-server architecture. This is probably the one you're most familiar with. Here you have an always-on server, usually sitting in some massive climate-controlled data center, complete with a permanent IP address. It just sits there, doing all the heavy lifting. The clients, like your laptop or your mobile phone, might connect and disconnect intermittently as you move around. The absolute key feature here is that the clients communicate exclusively with the server. They do not communicate directly with each other. This is exactly how the web, standard HTTP, and regular email work. Now contrast that with peer-to-peer, or P2P architecture. In this model, there is no central always-on server. None. Instead, everyday computers, your computer, my computer, directly request and provide services to one another. We are the peers. A huge, game-changing advantage of P2P, like you see in torrent file sharing, is its self-scalability. Every single time a new peer joins the network to download a file, they also bring brand new upload capacity to the network. It essentially scales itself. However, and pay close attention here for your exams, because professors love this, P2P is definitely not perfect. It faces three massive challenges. First, it puts serious stress on residential ISPs. You see, home internet is typically designed to be asymmetrical, meaning you get super fast download speeds but incredibly slow upload speeds. P2P demands heavy uploading from everyone, which can really clog up those residential networks. Second is security.
Because P2P is completely decentralized and open, it's inherently much harder to secure than a lockdown corporate data center. And third is the incentive problem. How on earth do you convince regular users to leave their computers powered on, giving away their personal bandwidth and storage to total strangers? So, your crucial takeaway here is fully understanding this exact contrast. Client server relies on a permanent middleman, which makes it way easier to manage, but it requires incredibly expensive data centers to scale up. P2P, on the other hand, is a decentralized, direct connection between constantly fluctuating users. That makes it incredibly scalable, practically for free, but it's notoriously complex to manage and secure. All right, moving to our fourth topic. We know how they are built, but what does an application fundamentally demand from the network underneath it to actually function? I want you to really think about this for a second. Does a banking app downloading a sensitive financial document require the exact same network treatment as you hopping on a live Zoom call with your friends? Well, the answer, of course, is absolutely not. As you can see, different applications have vastly different requirements. For a file transfer or checking your email, you need 100% data integrity. The network literally cannot drop a single byte of data, or the entire file is corrupted. You also need security, relying on transport protocols to encrypt that data so it isn't intercepted. However, these kinds of apps are usually elastic with throughput, meaning they'll happily take whatever speed they can get, and precise timing isn't really critical. But now consider internet telephony or streaming video. These are loss tolerant. If you drop a pixel on a YouTube video or a tiny fraction of a second of audio, our human eyes and ears probably won't even notice. But they are incredibly sensitive to timing. If the data is delayed by even a few hundred milliseconds, your Zoom call becomes an unworkable, echoing, frustrating mess. So, who actually handles these different requirements? That brings us to Section 5, meeting the two primary transport protocols. Grab a screenshot of this or write it down because this is a classic exam question. TCP, or Transmission Control Protocol, is your incredibly reliable, connection-oriented workhorse. It absolutely guarantees that all data will arrive perfectly intact and in the right order. It even includes flow control and congestion control so it doesn't overwhelm the network. We use TCP for things like the web and email, where accuracy is totally non-negotiable. Now, UDP, or User Datagram Protocol, is the complete opposite. It's the fast, unbothered protocol. It just blasts data out the door without ever checking if it arrived, and it completely ignores congestion control. But because it strips away all those heavy safety checks, it's lightning fast. That makes UDP the absolute go-to protocol for live streaming and internet telephony, where speed and timing completely trumped perfect accuracy. Okay, we've covered a lot of ground. Let's move into our final section and simulate a high-stakes Viva review session to really lock in this masterclass. I'm going to ask you a question, and I want you to mentally answer it before we reveal the text. Ready? Imagine your professor looks at you across the desk and asks you this exact question. What is the precise difference between a process and a socket? You need to be ready to explain the mechanics clearly without mixing up your terminology. You are going to confidently look back and answer that the process is the active program itself, the actual software running on the machine. The socket, on the other hand, is the interface, the gateway, or the door it uses to pass its messages down into the transport layer of the network. So one is the actor and the other is the doorway. Simple, right? Here is another incredibly frequent oral exam curveball. They want to know if you understand not just the textbook theory of network architectures, but how they actually interact with real-world physical internet service providers. The perfect answer here highlights the physical realities of consumer internet. You'll explain that residential ISPs give you really fast downloads so you can stream Netflix smoothly, but they give you very slow uploads. P2P completely disrupts this model by demanding heavy upload bandwidth from peers to share files, which inherently stresses the ISP's asymmetrical design. All right, as we wrap up, take a mental snapshot of this slide. These are the core high-yield principles you absolutely must remember for your written tests. Remember that apartment building analogy for IPN ports? Memorize those standard port numbers. Know the fundamental trade-off between TCP's careful reliability and UDP's reckless speed, and completely understand the structural difference in how client-server and P2P architectures scale. I'll leave you with this provocative thought to ponder as you hit the books. As fiber optics make upload speeds just as blazing fast as downloads, and as the smartphones in our pockets become just as powerful as traditional servers used to be, will the strict line between client and server eventually disappear completely? Will every single device in your home simply become an equal peer in a massive global network? Keep that in mind as you review your notes tonight. Thank you so much for joining me for this explainer, and best of luck on your exams. You've totally got this.